Okay, so let's go through the rest of magnetic fields in chapter 28. And so let's start, probably at the beginning of this range. A circulating charged particle. All right, and so the idea for this is that if you always have a force that acts perpendicularly to the motion, right, it can kind of behave as a centripetal force, right? If you think you have some kind of an object, and then maybe you have a force that's acting in, and it's always going to act perpendicular to the velocity, all right, the path you get is a circle, right? And so that's this, if we look at other locations on this circle, here, if we have a perpendicular, it's going that way. Over here, it's going to be going this way, and so on and so forth. All right, and so the magnetic force acts as the centripetal force. And so if we're going to hop right into uniform circular motion, well, we have the centripetal force was equal to mv squared over r, right? And this is just the definition of centripetal force, right? And just a reminder, centripetal force is a force that keeps an object moving in a circle. And so if you have like a mass on a string that you're swinging around, it'd be the tension in the string. If you have a car on a racetrack, it's going to be the friction between the tires and the ground. We can go all day. But here, we're going to have F sub B is, Q VB if everything's perpendicular. And that's going to be our centripetal force. So what we can do is we can set these two equations equal to each other. And we get QVB. And again, we'll keep this as the magnitude of charge, right? That way it doesn't matter if it's a positive or negative charge. That's just going to tell us whether we go clockwise or counterclockwise, right? So if we're just dealing with the circular path and not the direction of it, the charge doesn't matter. And we can set that equal to mv squared over r. Let's make this a slightly better v. There we go. Now that's some penmanship there. Okay. And so if we want to solve for the radius of this circle, well, let's see. We have a v over here, v squared over there. We want to bring this up here and then these down there, right? And so we have r is equal to mv over qb. And then this will be the radius of the path a charged particle takes in a magnetic field. All right. And so far, that wasn't too bad. We just took something we learned in the last lecture, something we learned last semester, and combined them. And so that's pretty good. So let's say we wanted to find the period, right? How long it takes to go into a full circle. Well, we have, let's just say time is equal to distance over velocity. If we're going in a full circle, 2 pi r. And so we could say the period is equal to 2 pi r divided by v. And we can rearrange this equation for v. And we get v is equal to QBR over m. And so we have our 2 pi r divided by that q br, and that's over m, so I'm just going to put the m up here. And look at that, the r's cancel. That's interesting. And so we end up with the period as 2 pi m over qb. And why is that so interesting? Well, the amount of time it takes for the particle to go in a full circle is independent of how fast the particle travels, right? That's extremely counterintuitive, right? Because in general, if I'm going to walk in a circle, how fast I'm going is directly related to how long it takes me to go in that circle. But that's not true for a charged particle in a magnetic field. All right, and so how are we going to kind of wrap our heads around this? Well, the key is in this equation. The radius of the circle depends on the velocity. So if you're traveling faster, you go in a bigger circle, such that the time stays the same, right? If you increase the speed, you increase the size of the circle, and it takes the same amount of time for a particle of the same mass, charge, and magnetic field to go in a full circle. And so that's a fun result. I'm a big fan of that. And then, we can always do the other games we play. F is 1 over t is equal to qb over 2 pi m. We have omega is 2 pi f. And so that gives us our qb over m. All right, and so that's if you want frequency or the angular frequency. Okay, and so that's all fine and good. And so this was kind of a special case in that if our magnetic field is going in or out of the board and our charged particle had some velocity that's going to bring it in a circle. That was just a terrible circle. That's the worst circle I think I've ever drawn. I'm going to leave it though. Right. But what were to happen if we were to take this particle and angle it slightly upwards? And this is something we can probably code together in lab this week if we want. That'd probably be a good exercise. You get, well, and so if, let me think of how I want to draw this. Well, let's think if we had a magnetic field, I guess I'll also label this as B, just so we all feel good. And we have some charged particle, we'll say it's positive, it doesn't matter. And we have a positive particle moving this way. What we can always do is get our V parallel and V perpendicular to the magnetic field. And what that's going to do is the V parallel isn't going to contribute to the force on the particle. Only the perpendicular was, because we do a cross product. And so if we want to do our right-hand rule, right, our pointer finger goes this way, our middle finger goes this way, and so our thumb's coming out of the page. And so we're going to have that particle kind of start forming a loop that starts out of the page, and then it's going to curve towards us, go back into the page, and then go away from us. But the whole time it's doing that, this parallel part, well, I wanted that to be red, but we'll be all right. This parallel part, it's just going to keep traveling in that velocity. And so what the particle's going to do is kind of do a spiral in that velocity where, like I said, it's going to come, out of the page over here, into the page over here, going to go this way, that way, this way, that way. All right? And so that's what our particle is going to end up doing. And we get a helix. Okay. And so let's start trying to dissect that a little bit. And so, actually, I don't know why I deleted all that. That was a mistake. And so what we can do is if we define this angle to be phi, well, I guess we could probably pick a better way to do that. I guess this angle would be phi, such that phi is the angle between the magnetic field and the velocity. So when we go ahead and find F equals Q VB sine phi, we have our phi there. And so let's see. We could say V parallel is going to be, well, so V parallel is going to be this one here, and so it's going to be V cosine phi, which means our V perpendicular is going to be V sine phi, and there we go. And so what can we do with this? If we want to find the pitch or the incline we get from our charged particle going through this field, all we do is we know the period it takes to go in a full loop, and the pitch is defined to be how high you climb for a full loop, right? And so if we know 2 pi m over qb is the period, well, let's see. We were trying to find how high it climbs when it does a full loop. Well, so V parallel, all right, it's going to travel in that direction. And so if we want to get to a distance, we have distance is equal to V over T, right? Nope, V times T. Whew, that was close. Right, meters per second times second gives us meters. And so we could say V cosine phi times 2 pi m over qb is going to be the pitch, right? How high we climb. Okay. I think that's good for that. And so then let's hop into chapter 28, section 7. Cyclotrons and synchrotrons. Just some straight up sci-fi jargon. Okay. And so I think to start, we're going to go with the cyclotron. I think essentially we're just going to go through the cyclotron. And let's see, what is a cyclotron? Great question. I'm glad you asked. And so essentially what happens is you have two plates that are perfectly drawn, and they're hooked up to an AC power source, right? And so what we can do is we can apply, a voltage across this plate that we can then flip as desired, okay? And so we're going to take our charged particle. I'm actually going to make this one the negative to start. V negative, and then I guess V positive. Look at that, I just completely changed the notation. All right, and so we're going to start with a positively charged particle. And let's see, well, if these plates are charged, we're going to have an electric field, right? We can go through and we can look at this and say, this is all negative on this plate, all positive on this plate. Right, but that's going to get messy if we do that. Look at that, it's already ruining everything. And so what we're going to do is we're just going to say we have an E field going this way. And so what's that going to do? Well, other thing to keep in mind is that there is a uniform magnetic field across all of this. We should probably make our charged particle a little bigger. All right, and so if this is our electric field going this way, right, charged particle and electric field, we get F equals QE. It experiences a force. If it experiences a force, it experiences an acceleration. All right, and so this charged particle is going to start moving, right? And so let's say it starts heading this way. Well, now we have a charged particle entering a magnetic field, right? And actually, what we're going to do is I'm going to kind of delete the magnetic field in here, just to make life a little easier in how we view this. Right? In reality, these plates are so close together that it's essentially like nothing happens in between them as far as the magnetic field goes. You still get the acceleration from the potential, but they're so close to each other that you don't have a chance to really change the path direction. But we'll see what happens when we get into here. And so, right, we accelerate till we hit this plate. Right, this whole plate's all at the same potential. Where did we go? This whole plate's all at one potential. And so once we get there, we stop accelerating. And so let's see, if we say V is this way, B is coming out of the board, so we put our pointer finger with the velocity, our middle finger towards us, we get a force that goes up, right? And we know that force is going to go up and it's going to curl, right? The path is. And so we kind of do one of these until we leave that plate. And so this is set up to be timed, right? You got a bunch of fancy electronics up in this here. What happens is the moment we leave this negative potential plate, it becomes the positive potential plate. And so then we get an electric field that goes this way, and our charged particle accelerates again. And so now we have a slightly higher velocity as we shoot through here. And so we said before that as velocity increases, so does our radius, right, for the charged particle in the magnetic field. And so we get a bigger curve, right, because it's going faster. And so then once it comes out of there, guess what happens to the plates? You got it. They flip again. And so the electric field flips again. And so we accelerate once again. And so now we go this way. And we were going faster again, so we travel in a bigger arc. And then they flip the plates. I forget which is, I think this is negative now. Yeah. And that flips the electric field, which flips our acceleration. And so now we get a bigger arc, and we just keep doing that, right, until we go faster and faster and faster. And then eventually our particle zips out the side, going extremely fast, or as fast as we need it to be, right? And so that's the essential working mechanisms of a cyclotron. I don't think we really need to go through the synchrotron. If you followed this, you'll follow that. It's 2 paragraphs in the book, if you're interested. Right, but essentially what this does is it uses cyclotron, uses, I was going to say constant, I'm going to say uniform. Also, let's make this purple. Uses uniform magnetic field and alternating, I was going to write out the word electric. That's an E field. To accelerate a charged particle. And I know what you're all thinking. You're all thinking, Dr. Dillon, why do we have to bring in a magnetic field to this? Surely, all we had to do was get these 2 plates, put them far enough apart with enough potential, and we will accelerate our particle as needed. And that's true. That's correct. But the issue being, either one, you would need an incredibly high potential to be able to do this in a confined space, or it would have to be really big, right? And if you think all the acceleration happens between these plates, it's happening thousands of times, in a really big cyclotron. And so even though it's a very small distance, it keeps happening. And if you were to stretch it out, then all of a sudden, yeah, you could get the same result. If you have your positively charged particle we started with, and you have maybe some kind of a parallel plate set up. But, who wants to go all the way over here? Look at that. We don't even see the start anymore, right? And it's just you'd have to do something very big to be able to get the same result, the same acceleration, or to get to the same velocity, right? And so what they do is they essentially found a way to, by continually flipping the potentials, able to confine this acceleration, right? And so that's the goal of that. And so now let's get into something fun. Not that we weren't in something, it's all fun, it's physics. So 28.8 is the magnetic force on a current carrying wire. Okay. And so, well, what is a current? Moving charges. And we've had a couple definitions of current. I think we said it was the flow of charge. We've said it's dq dt. But at the end of the day, it's a bunch of charges moving together, right? Okay. And so if we have a current in a magnetic field, we have a bunch of moving charges in a magnetic field, and we can get some kind of forces on them. And so let's see. Let's have kind of 3 setups. Okay, so we'll call this A, we'll call this B, and you guessed it, this one's C. And so we'll go ahead and we'll have some kind of a magnetic field. Whew, that's a terrible dot. You didn't see that. Pretend that never happened. We'll have the same thing over here. And again, right, this is perfectly uniform. Everything's drawn wonderfully to scale. And don't come at me. Okay. And so we have the same setup in each case. The dotted line's going to be what would happen if there's no current in our wire. What color are wires? I guess we'll do, I don't want yellow. We'll go green. That's a gross kind of a green, but we'll be all right. And so if the current is equal to 0, right, there's no net movement of charge. Ooh, can I like... Well, all right, I was going to see if we can make like a wider tip, but that's something for me to figure out later. And there's our wire. All right, and so that's all fine and good. But now let's say, what if our current is going up through the wire? Well, we would have V is going up, B is coming out of the page. And so if we point our pointer finger up, middle finger coming out of the page, we get the forces to the right. And so what's going to happen is if we have a high enough current, high enough magnetic field, all that together, the wire itself will bend, right? And I guess maybe for this to be a little bit better of a picture, we have more magnet. That way it's kind of centered a bit. I drew it slightly off center. Right, and so the wire will, excuse me, the wire will bend with the wire because of the force it experiences. Now, if we were going to have the current going the other way, now the velocity is down, the magnetic field's still out of the page, so if we point down towards ourselves, middle finger comes up, we get the forces to the left, right? Shouldn't be a huge shock. You flip one of the vectors in a cross product, you just flip the result, right? Same as if you had a negative charge, then you would have everything flipped. But we're dealing with conventional currents here, so it's the flow of positive charges. Although, go ahead and see what would happen if you had negative charges flowing the opposite way in each of these cases, right? See if you can justify our use of a conventional current over an electron current. All right, the force would be to the left, so the wire is going to bend out that way. All right, and so, nothing too illuminating so far. But interesting, right? And so let's try to tackle this with some math as well. Well, first, let's draw a more microscopic view of this. We said wires are green today. And so let's say if we zoom in on our wire, we still have our uniform magnetic field. Okay. And then we're going to kind of just take like a representative chunk of wire. And that's some length L of wire. Okay. And we're going to have our charged particle moving through the wire. And I think the book goes through and tackles this for a negative charge. We're going to say we have a positive charge. I think they do. We have a negative charge that moves the opposite direction of the current, and so it's fine. We're going to do it with a positive charge just so life's easier. We get the velocity is going to point this way. All right, same direction as the current. And if we want, we can go ahead and say that's the drift velocity. And so what do we have here? For when it was going up, the force was to the right, which, we can go through and do it again. So velocity is up, magnetic field's out of the page, pointer finger goes up, middle finger comes out of the board, and we get the force to the right. Yeah, and I guess we'll... No, I don't want this to be the same color as the magnetic field. That's crazy work. Pink is a great color. And so we're going to have this be the force of the magnetic field. And I guess if we want, we can go ahead and label the magnetic field. And there's a good picture that we have. I'm going to go ahead and erase this so we have better use of our space. And so, well, if we have the amount of time it's going to take to get through this whole thing is going to be how long it is divided by the drift velocity, right? Length divided by velocity gives you time. Okay. So let's see, we can also go ahead and say charge is equal to current times time, right? If you sum out amps per second, or if you have amps, which is coulombs per second, times an amount of time, you get the total amount of charge built up. And so then we can combine these two, and we get Q is equal to IL over our drift velocity. Oh, I guess we'll make this a lowercase d so everything's consistent. And okay. And so if we have our standard equation for the force of a magnetic field is QVB sine phi. If we want, we can plug in our Q. And we get the force is equal to, let's see, we said Q was IL over the drift velocity. Well, V, that's the drift velocity, so we get that again. And then we have a B. And let's see, what are our angles? Well, phi is equal to 90 degrees because our velocity is perpendicular to the magnetic field. And so sine goes to 1. Okay, and look at that. We can cancel this out. And so we get the force is equal to ILB. Okay, well, that's fun. And so that was true when everything was perpendicular. Were it not perpendicular, we would still have this sine phi in there. And so we can say F sub B would be equal to ILB sine phi. Or if we want to be a little better, the magnetic force on a current carrying wire is going to be IL, where L is a length vector that has a magnitude of the length of the wire within the magnetic field and is pointed along the direction of our current. And so we have IL cross B. And we can put a box around that because that's an important result. And this will be the force on a current. I mean, we can say current carrying wire. We can just say on a current. In a magnetic field. And let's see. And so I is going to be the current. L, length of wire within B field. And then B is B. Right, and there we go. And so then we can also get into some funky scenarios where what happens if the wire's not straight. And let's see, what would we have to do? We'd have to come up with some kind of path integral, right? We would have to figure out a way to integrate along the wire. And so we could say DFB is going to be I times DL cross B. And so that's going to be the case that we don't have a nice perpendicularity, or if it's not a straight wire. Okay, and so that's all fine. That's good so far. And let's just keep on trucking. And let's see if we can find the torque on a loop of current. I think the book says torque on a current loop, but, you know, same difference. All right, and so the idea here is going to be something very similar to how motors work. And we can make a little motor in class on Wednesday. If someone reminds me, I'll build a motor real quick. You know, just kind of craft one up. And so let's see. So if we have, you know, some magnet. Yeah. We're just going to have the North Pole here. We all know there's a South Pole elsewhere. Right. I mean, well, I say elsewhere. It's over here, and then another North Pole here. Or I mean, if we want, we can make it like a horseshoe magnet. All right, we could do one of these, but you know, that's a pain, and so we are just going to leave it as north over here, south right there. And so if we were to draw the magnetic fields, it's going to be like this. We said wires are green today. And if we were to kind of have some kind of a loop of current, see, and this is again where I hate two dimensions. Let's see, I want this to be kind of in and out of the board. And so yeah, that's good enough, I guess. And let's say it's sitting in something so that it's free to rotate if needed. Let's say we have a current going around here, coming back through here. All right, and let's try to see what the force is going to be. I'm going to go through and I'm going to label these 1, 2, 3, and 4. With the idea that if we can find the force on all 4 of the sections of wire, then what we can do is we can find the total force and torque on the wire. And let's see. So in section 1, we have the current going this way, and the magnetic field's also going this way. So we can say F1 equals 0 because they're parallel and it's a cross product. Same argument, F3 equals 0. Okay. And so then we just got to kind of look at F2 and 4. And let's see. So if we have the current going this way, magnetic field going this way, pointer finger goes in the direction of the current because that's our velocity. Middle finger goes with the magnetic field because that's what it is. And our thumb points down. And so we get F2 points down. And then we do the same thing for F4. Our velocity's going this way, magnetic field's going this way. So our pointer's coming kind of out of the page. Our middle finger's going towards the South Pole. And we get our thumb points up. Well, if you can imagine if this is free to spin, right? And so, right, if it wasn't free to spin, then you go, oh, some of the forces is 0, but it can rotate. And so it actually matters where these forces are and how they're going to spin. Right? Common misconception. People look at this and they go, oh, the sum of the forces is 0. And it's true. It's not going anywhere. It's not traveling, but it's rotating. You have torques and moments. Okay? And so we could say, what could we say? F2 is going to be ILB, maybe a negative since we have it going down. F4 is going to be ILB. And so the torque's going to end up being, related to that. Let me see. I'm trying to see if we want to really go through the derivation they have in the book for this. I think this might be okay for now. And then, we had everything be perpendicular and nice. And then if we think about this, well, if this rotates a bit, it's, no matter how we rotate this, the current's always going to be perpendicular to the magnetic field. And so we're going to get this, always has this torque on it, or always has these forces on it. Okay. And so I think that's good for this section. Yeah, let's hop into the magnetic dipole moment. And so the main takeaway from this is that if you have a loop of wire in a magnetic field and it's free to rotate, it will. And that's just the general principle in DC motors. If you want to build an AC motor, you have to do some more complicated things, but it ends up being a little more efficient. And then we have equations for the torque on a current carrying wire in a magnetic field. And I think for the most part, you're fine with just using the result that you get of tau is equal to Ni pi r squared times b sine theta. With the idea that the more loops you have, the greater the torque, right? If you take a coil of wire, you get a more drastic result than if it's just a wire. Yeah. And so I think this is a fine result to just kind of skip to. If you really want to see the derivation they do in the book, that's fine. But this is good enough for now. And then let's hop into 2810. Magnetic dipole moment. Actually, give me 1 second. Okay, yeah, so we're going to wrap up with the magnetic dipole moment. And I guess to get started with that, we'll start with 2 loops of current. Going these ways respectively. And we want to find, well, and we'll say both of these are in an external magnetic field. Yeah, it's pointing up. And so we want to figure out which one of these is a higher energy and which is a lower energy, right? And in general, lower energy means happier. It's easier to exist that way. And so we want to figure out what direction the magnetic field is going to point for each of these currents. And so we can use a right-hand rule for that. We're going to use one of the ones where you curl your fingers, and your fingers are going to curl in the direction of the current, and then wherever your thumb points is what the magnetic field does. And so for this one on the left, if we curl our fingers that way, our thumb points down. And so we can say the magnetic moment for this is pointing down. And over on the left, we curl our fingers the other way, and we get that it points up. And just like if we were to have bar magnet, and we kind of glossed over it before, but inside the magnetic field points this way, and then outside we get our loops pointing like this. Right, and so we get that the magnetic field goes through the magnet, right? Like that was on the side. And so this magnetic moment is going to want to align with the magnetic field to be happiest. And so this over here is going to have the high energy. And over here we have the lower energy. Right, and of course when I say high and low, it's relative to each other, right? We don't have any actual numbers or values, but compared to each other, left is high and the right one's low. Okay. And so if we want, we're given mu is equal to Ni times A, right, the area of that little loop of wire. Okay, which we can use this definition up here. All right, Ni, and here's the area of a circle. And so we can say the torque from that is going to be mu b sine theta. Right, where theta is the angle between the vectors, or if we want, we can say tau is equal to mu cross b. Right, which should be very similar to what we had for an electric dipole, which was tau is equal to P cross E. Right, and that was for a dipole moment. And an electric field. And again, we should specify it's an electric dipole. All right, here we have a magnetic dipole. Okay. And yeah, and so again, if we really want to start diving into the weeds, we could have U as a function of theta was equal to negative P dot E. And here we can have the energy to hold a dipole in a magnetic field is going to be equal to negative mu dot B. Right, and so, if you wanted to hold, let's say you had a electric field that's doing this, and you had a dipole that's doing that, right, it would want to orient itself like this in an ideal world. And since it's not the way you're gonna, it prefers to be, it takes a potential energy to hold it there, right? And that's kind of where we're getting to the heart of potential energies, right? If you're holding a block at the top of a cliff, right, if nothing was stopping it, it would be at the bottom of the cliff. If you have a compressed spring, right, if there was nothing compressing it, it would just be at its unextended length. So anytime you're holding something where it wants to move and you're not letting it, that's where you get a potential energy. And just like here, over here, right, where this wants to be kind of flipped around, you're going to have a potential energy associated with that. And that's pretty much all that is. Yeah, and so I think that's that for this one.